Look up at the night sky, and your eye notices the multitude of bright stars shimmering so far away. These stars are massive objects, almost out of range of our comprehension in their size and energy. But there is a more potent object out there, an object so massive a star next to one is practically insignificant. This object has an incredible amount of mass compressed into quite literally nothing, into a single point so dense that it rips apart the very fabric of space and time. Around it, our universe as we know it breaks down. It laughs in the face of Newton's equations, and even Einstein's relativity has to struggle to comprehend such an object. To help us explain, we have Dr. Philip E. Carrott, Professor of Astrophysics at the University of Iowa.
Well, if you go back to the black hole, is like the kindergarten definition, which is, nothing, not even light, can escape. Okay, then that sentence, basically, for that to make sense, it implies that the speed of light is a fundamental maximum speed. In Newtonian mechanics, you have things like, instantaneous action at a distance, and you don't have the speed of light as a fundamental speed limit in the theory. And so if you allow objects to go at arbitrary velocities, you never have a black hole, because you can always just go faster if you want to escape it. So that's so from a fundamental reason, you have to have the speed of light come in here just to get the idea of a black hole to start off with.
A black hole's gravity is so stifling, even light is tugged back into its mold. There are only 3 values we have to define the properties and features of the black hole. This is the no-hair theorem. While surface features like clouds on planets or hair on humans can identify individuals, there is no such visible way to distinguish between black holes. However, these 3 numbers, mass, spin, and charge, organize a classification system for black holes, with each category bearing the name of a physicist that describes such a combination of these numbers. The simplest black holes don't have spin and have no charge. They are just a point of ridiculous mass in infinitesimal space. These are Schwarzschild black holes and are the easiest to describe mathematically. Now, if the hole is spinning, this affects properties like the event horizon, and the hole is called a Kerr type. A black hole that isn't spinning, but does have some electrical charge, is a Reisner-Nordstrom black hole. The most complex black holes have both spin and charge. These are known as Kerr-Newman holes. For a dying star to collapse into a black hole, the mass of the star must be higher than a benchmark called the critical mass, above which the star's gravity will win out and turn it into a black hole. The accepted value among physicists is approximately 2.95 solar masses for the core, or 8 solar masses overall. When a smaller star than the critical mass dies, its outer layers billow away and a dense white dwarf or neutron star is left over, but not a black hole. When a star is well above the critical mass, its death is violent. What is left over, a single point singularity of infinite density. A black hole has been formed. The point where a black hole becomes black is known as the Schwarzschild radius, and is given by the equation R equals 2gm over c squared. For Earth, this radius is 8.9 millimeters, and for the Sun, it is just under 3 kilometers. To get a better image of just how dense matter has to be at the Schwarzschild radius, let's get an idea of how much mass is in the Earth. A grain of sand is roughly 1 cubic millimeter, and a volume of sand is about 1/2 empty space. So a cubic millimeter has 5 times 10 to the 8th grains of sand. Iowa City is 6.3 times 10 to the 7th square meters. Thus, to cover Iowa City to a depth of 1 foot in sand would take 1 times 10 to the 16th grains of sand. A fully loaded oil super tanker is 1/3 of a kilometer long and weighs about 655,000 tons, which is 5.94 times 10 to the 8th kilograms. The Earth weighs almost exactly 1 times 10 to the 16th times greater. In other words, 1 times 10 to the 16th oil tankers of mass 5.94 times 10 to the 8th kilograms would be equal to the mass of the Earth. Now take those 1 times 10 to the 16th oil tankers and condense them into a radius of 1/3 of an inch. And now you have the density of a black hole. In order to comprehend the properties of a black hole, Imagine that the mass of the Earth were crushed to a point, that its matter were packed so tightly that even its atoms could no longer withstand the crushing pressure and collapsed. When everything contained within the Earth's 12,742-kilometer diameter is compressed to fit within a diameter of 5 centimeters, its density would be equivalent to the density of a black hole. This golf ball-sized Earth would still possess the same mass and gravity of Earth, however.
Black holes are typically very compact. A stellar mass black hole, the event horizon is only tens of kilometers across, and so it's an extremely compact region. But yet it's releasing far more energy than our sun does, or the power rate is far greater than our sun.
When trying to explain this level of gravitation, Newton's laws failed to quantify a feasible solution. The ability to find solutions was eventually discovered by Einstein in his general theory of relativity. As Professor Carrot would say, the surface of the Earth is an extremely good approximation to Newtonian mechanics.
But as you get to more and more intense gravitational fields, it gets worse and worse. And it breaks in, and the divergence between Newtonian predictions and general relativistic predictions become really strong when you actually get close to the surface of a black hole.
General relativity explains gravity as the warping of space-time, similar to how a bowling ball warps a trampoline. Other objects are then subject to this warped feeling and fall into this depression. A black hole is so massive and so dense that it warps space-time to an infinite degree, creating a real, bottomless pit. The influence can be so strong that space-time can even be warped into a swirling vortex.
Okay, well, this somehow seems more novel to people, that black holes actually can rotate. But if you form a black hole from matter that has net angular momentum, it itself has net angular momentum. If you now have a rapidly rotating black hole, you can actually orbit closer in. Okay, because as the black hole is rotating around, it's actually dragging space-time along with it. Okay, so now the particle, even though the particle can only go at the speed of light relative to space-time, it's now actually going faster than that from the point of view of an outside observer, because it's going close to the speed of light relative to space-time, but now the space-time is being dragged around. Okay, so if you have a spinning black hole, you can actually orbit closer in, so you can get higher speeds.
This whole phenomenon is called frame dragging. Think of a spinning black hole as a massive whirlpool, and a photon as a kayaker attempting to escape. Not only does the kayaker have to overcome the force of gravity pushing them down into the depression of the whirlpool, but they must also overcome the spinning current of water through which they are trying to move.
Imagine that this were a black hole. Inside the black hole, inside the event horizon, you can imagine light trying to get out, pointed outwards, trying to get out. But space itself is falling faster than light and drags light itself inside the black hole.
Like this video, everything in the universe, including black holes, is required by the laws of physics to become more chaotic with time. This is the second law of thermodynamics, which we have experience with through the magical, hidden force of friction. To many, the black hole seems to embody a contradiction to this law. How can something that consumes everything around it, in essence bring order to chaos, in turn have entropy change of its own? The answer was Hawking radiation. Hawking radiation was discovered when Stephen Hawking took a simple fact of quantum mechanics, the vacuum foam, and asked what would happen to this effect at the edge of a black hole. The answer was a revolution in black hole physics. But let's start at the beginning. Quantum mechanics dictates that no one can know the exact energy state of anything, including nothing. This means that not only can we not know everything about particles, but we cannot know the exact energy state of the vast vacuum that is space. And hence, we have the quantum foam. At subatomic levels, the universe gives birth to pairs of virtual particles, one with positive mass and energy, the other with negative mass and energy. These particles will exist momentarily before colliding and annihilating each other. This happens over and over at every point in space and time. Still confused? Let us demonstrate. These two researchers, like particles, appear out of nothing. They zoom off away from each other for a small time. Then they will be drawn back toward one another until smack, they collide and annihilate. But let's ask ourselves the same question. What happens when these particles burst into existence too close to the edge of the event horizon of a black hole? No answers? Fortunately, Stephen Hawking already knows. The answer is that the particle with positive energy will escape the event horizon, leaving its negative partner to the endlessness of the black hole. This negative particle is consumed by the black hole and has very serious consequences. Thanks to Einstein's E equals mc squared, we know that the mass and energy are directly proportional, and since this particle had negative energy, it also contained negative mass. And once consumed, it will actually decrease the mass of the black hole. The other particle, without its partner to collide with, leaves the vicinity of the black hole and will eventually reach Earth, where they will be detected. And boom, in one thought, we have changed the black hole from an everlasting, dark, empty object into a monster of finite existence that isn't as invisible as we once thought. So why haven't we started finding black holes using this new radiation signature as a guide? We were hoping you wouldn't ask, but since you did...
When the Big Bang occurred, there may have been little localized spots of matter where the matter was much denser to actually form black holes directly very early on in the universe. Okay, and so the only chance we have of seeing Hawking radiation, if you actually look at Hawking radiation is extremely dim for any astrophysical black hole. I mean, it's much less than the radiation you get from just matter falling into it. Hawking radiation is actually more intense the lighter the black hole is. So if you have a black hole that actually is producing Hawking radiation, it actually loses mass because it's radiating energy away, and it gets lighter, so then it actually radiates faster. And so if you had one of these so-called primordial black holes, every so often, depending on how massive they were and exactly when they were created, they should just evaporate in a little puff of gamma rays.
Black holes have seen the re-evaluation of physics, from the destruction of Newtonian mechanics by general relativity, the introduction of Hawking radiation, the exploration of supermassive objects, of spin, and of the very fabric of the cosmos. Black holes have been at the heart of it all.
When black holes were first thought of, and when I first started studying black holes, even I remember thinking, oh, a black hole, it's the end of everything. A star collapses down and everything disappears into it, and nothing ever comes out, so maybe it's really boring. But really, black holes represent our best way to have an ultimate test of the physics of understanding the universe.